Sakura, and I want to thank also all the organizers for having me here. And for putting together such an inspiring conference. So my title is a little bit provoking maybe, but I'll put a lot of asterisks here, and I will explain what they are and how this might at all make sense. But first, a few of claims that, first of all, this talk I have given it at the UQM meeting in January. So for people who was there, this is the same talk. If I have time, I might get to something new we're doing, but I probably won't. It's actually a shorter talk. So this is more or less the same talk. But I also realized that a lot of the formalism, the tools have been in development for decades by people in this room. So, and if I miss any of the references, please let me know. I'll make sure to add them next time I give the talk. But other than that, this is a talk. This is just me, I think, as a way of trying to understand what, as a mortal condensed matter theorist, we can do using this whole generalized symmetry framework. What kind of question can we answer other than just admiring at the beautiful framework and all the mathematics associated with it? Okay, all right. Okay, and as you see, I put a sandwich here because I'm going to make a lot of use of that, and I'll explain, not so much, I know this audience probably know a lot about symmetry TFT already, but I'll try to explain what my notation means just to be sure that we're on the same page. Okay. All right, so let me first explain a little bit about the asterisks. So I put asterisks on R, on all, and symmetry breaking. So when I say all star transitions, I mean not all the transitions you can think of, but a subset of, well, a pretty large subset of interesting transitions that condensed matter people might be interested in, like especially transitions between gap phases, like SPT phases or topological phases, something that can fit into the sandwich structure. Of course, that's not a definition, but I'll try to illustrate what can be, at least in the simplest way, can be fitting to a sandwich structure. And then by symmetry breaking, I'm being more general with the notion of symmetry, because the notion of symmetry has now been generalized to a very extensive, very large extent. It includes breaking of higher form symmetry, non-invertible symmetry, categorical symmetry, all sorts of generalized symmetries. And finally, R, by R, I don't literally mean that they are. I mean that the critical point is more or less the same critical point up to reorganization of some sectors. So it's, to a great extent, it's more or less the same thing, except that some of the sectors might need to be recombined. Okay, so back to the story of Landau. So this is Condensed Matter 101. Condensed Matter says that we want to understand phase and phase transitions, and we want to understand universal properties of phase and phase transitions. What kind of, when do we say things are in different phases, and when do we, how do we understand what happens at the critical point between the transitions? So Landau says back in the days that the simplest way of understanding things is using the principle of symmetry breaking. That if the system has a symmetry, can be well, back in the days it was more of the normal symmetries like translation, spin rotation, time reversal. And if we have those symmetries, but somehow the system at hand doesn't preserve that symmetry, doesn't necessarily preserve that symmetry, then we can be in a variety of different symmetry breaking phases. So there's a difference between symmetric phase and symmetry breaking phase. And here I put simple symmetric phase and simple symmetry breaking phase just because now we know so much more than those simple-minded product state kind of symmetry symmetric and symmetry breaking phases that I'll mention in a minute. Of course, the progress of the past decades is that, many decades, is that now we understand many more phases that's beyond this framework, including autofractional quantum Hall, when people start saying, oh, the system doesn't need to have a specific symmetry, and the different Hall plateaus are not differentiated by how they break the symmetry. And then we have SPT phases, which all have the same symmetry. They don't break the symmetry, but they're still different phases. And then fractal phases, you heard Mike talk more about that yesterday, symmetry-enriched topological phases, and some gapless things like non-Fermi liquid. So this has been celebrated in the past few decades as a big advance in condensed matter in terms of how much more now we know about different phases. And of course, the question is, then what is the bigger framework to capture all these phases and hopefully also their transitions? Because these lists of new phases, we feel like we have a good understanding of them, and we'll hear talks at this conference about trying to prove that these are all the phases we have in some cases, in some dimensions maybe. So we're actually pretty confident about how many are there and how to enumerate them, things like that. But in terms of whether there's a bigger framework to say, oh, they all fit into that, and there's not something like the Landau paradigm that's so systematic. But the progress has been that the notion of symmetry has been greatly generalized, back to the paper by Entang and Nadi and others here. And I learned this from a paper by John McGravy, which is a very nice review paper talking about this notion of generalized symmetries. And it turns out that, one very important example talking this paper is that once we have generalized so-called, for example, high-form symmetries, then some of the seemingly non-symmetry related phases, like topological phases, like quantum Hall or toric code, things like that can also be thought of as some kind of symmetry breaking phase. And the fractal one is more exotic, and maybe it's related to some subsystem symmetry breaking. Okay, so that's about phases. But I want to mostly be talking about phase transition today, or in other words, relations between phases, and related to that, the phase transition. So the one that Landau understands is the one that's from simple symmetric phase to so-called simple symmetry breaking phase, where the remaining symmetry is a subgroup of the original group of symmetry. And it's very well understood that what changes from one side to the other is that the autoparameter originally has to be 0, now it's not 0, and it fluctuates across the transition, and the correlation function of the autoparameter changes quantitatively, and because of all these intuitive picture of what can happen at the transition, and using the autoparameter as the key, Landau says that the transition can be continuous. It doesn't have to be, it may not be, but it can be continuous, and we can write down some field theory using the autoparameter as the low energy degree of freedom, and if lucky, then we can do something about the field theory and actually get the critical point. So this is the program. Okay. So other than that, there's another case that directly follows from the simple symmetric phase to symmetry breaking, which is the SPT to symmetry breaking, because the same autoparameter idea still applies, so everything directly follows. But other than that, the other phase transitions between the phases that I list on the previous pages, they don't immediately fit into the framework. For example, different symmetry breaking phases with the subgroup, where the subgroup on one side doesn't fit into the subgroup on the other side. And this is, of course, famously this DQCP transition, where people propose a different mechanism where at the critical point there's some deconfined fractional thing going on, such that that provides a new mechanism for the transition to be possibly continuous, although it might not be. But it's possible, in principle, that this transition can be continuous, and there's some field theory description for it. Okay. Other than that, there can be transition between SPT phases, topological, non-topological phases, and different topological phases. There's tons of study already on different examples, cases. You can find a lot of papers in the literature talking about different transitions. But what I'm hoping for here is that maybe there's a more generalized version of Landau paradigm such that these transitions can all fit into the same framework. Okay. So with the understanding that some of the topological phases can be understood as symmetry breaking of higher form symmetry, then the transition between topological and non-topological phases actually has the hope of becoming just higher form symmetry breaking, although with higher form symmetry breaking, the tricky thing is that the autoparameter is a non-local object, so it's harder to deal with. If you write down some field theory, it's harder to deal with it. But there's something we can do. It's just not easy to deal with. Okay. And the question is for the other ones, like in the DQCP case or SPT transitions, whether there's similar mapping people can do that take them also into a symmetry breaking form. Okay, so most of the thing I'll be talking about is 1+1D, and if I have time, probably I won't. I might talk about 2+1D, but I want to just first explain the framework in 1+1D. And if I'm done with that, I'll be happy. So in 1+1D, we know a lot, just because it's simple. So we do know in a lot of cases how to deal with transitions. For example, we can talk about the transition between 1+1D trivial superconductor to the non-trivial topological Majorana chain. And this is a example taught in a lot of lectures where you can apply Jordan-Wigner transformation to map it into the spin chain, where the spin chain, in the spin chain, it becomes the symmetric phase and symmetry breaking phase, and the transition become a symmetry breaking transition. So that's nice. Although originally it's not of the symmetry breaking form, it's a topological transition, but after the mapping, it becomes a symmetry breaking transition. And there are other examples, and this is an example of 1+1D Z2 cross Z2 SPT transition, where we take the trivial and non-trivial SPT phases, but after the famous Kennedy-Tasaki transformation, which is a non-local big transformation, just like Jordan-Wigner, it maps the phases to still have Z2 cross Z2 symmetry, but on the one hand, it's a trivial phase. On the other hand, it's the symmetry breaking phase. Okay, so the transition between two SPT phases after the KT transformation, it becomes the spontaneous symmetry breaking transition of Z2 cross Z2 symmetry. Okay. And there are more. This is a DQCP example where we have Z2 cross Z2 symmetry, but the symmetry has some anomaly. The symmetry is somehow wrong, which means that there cannot be a simple symmetric phase with the symmetry, but there can be partial symmetry breaking phase, like a partial symmetry breaking to the first half of the Z2, or partial symmetry breaking to the second half of the Z2. And then shown in, especially Caroline and Michael showed that there's a very nice mapping such that it turns into the transition between a purely simple Z4 symmetric phase to a Z4 spontaneous symmetry breaking phase. Okay. Yes.
So this is like gauging, basically, right?
Right. Yeah. Yeah. So in this symmetry, I will show the symmetry TFT picture, and these are basically gauging. Yeah. Right. So especially when Jordan Wigner and Mechanics of Society was proposed, it's not obvious that they all fit into some framework, but now together with more examples, we'll see that this all becomes something that we can do in the sandwich. Of course, the sandwich has a long history, so hopefully I'm citing enough papers here, but maybe not. And what I need to say that when I'm drawing the sandwich, it's I'm drawing only the spatial dimension, because it's not a person. So this is the the spatial slice. The bulk is a d plus 1d topological bulk. At the top boundary is a gap boundary where some certain condensation happens on the top boundary. And then the bottom boundary is left open to have dynamics. And then on the topological operator floating in the bulk, they become the topological symmetry operator. And then the top boundary tells you which symmetry operator actually becomes not quite a symmetry because the condensation already fixes some of the symmetry operator into certain sectors. And then the last important thing is that when the top boundary is chosen and then the symmetry is determined, then we can have things tunnel between the top boundary and the bottom boundary. And the thing that tunnel can carry symmetry charge because they cross with the symmetry line. So these can be the charge operator, while all the dynamics that happen on the bottom boundary is automatically symmetric because it happens very far away from the symmetry operator. Okay. And then finally, we squeeze it into something with finite height and becomes effectively a d-dimensional system. So the simplest example is, of course, the 1 plus 1d Z2 Ising chain, realizing such a setup where we have the 2 plus 1d toric code in the bulk. And then on the top boundary, we can just simply have the gauge charge of the Z2 gauge theory condensed on the top boundary. And then the string operator of the gauge charge becomes automatically 1 because of the condensate. And then the other string operator, which related to the gauge flux, is left to take value in plus minus 1. So that becomes the effective Z2 symmetry in the setup. This might be too naive for some part of the audience, but let me just go through it to make sure I'm consistent with myself. And then vertically, we can still have the gauge charge tunnel, and that anti-commute with the M string operator, and that becomes my charge operator for the Z2 symmetry. Okay. And to realize some gap faces, I can choose the bottom boundary to be in a gap state, to be in the E condensate and the M condensate. So these are two different gap boundaries of toric code. And they will correspond to different gap faces of the Z2 Ising chain. And to see which gap phase it realizes is actually easy to notice that the difference between the E condensate on the bottom and the M condensate on the bottom is that if we tunnel a charge, if we tunnel an E from the top to bottom, it can disappear into the E condensate here, but not into the M condensate there. So there's actually this autoparameter actually keeps it in the ground state for the E condensate. So this is on this side, this is the Z2 symmetric phase, while this is the Z2 symmetry breaking phase, where if you add a charge, you don't get out of the phase. You have a ground state generously because of that. Okay, so this is very simple. And associated with that, we have the 1 plus 1d P-wave superconductor. And that only takes a very slight modification of the picture to achieve, where we still have the 2 plus 1d toric code in the bulk. It's a topological bulk. But we can have a different top boundary, where the top boundary is so-called fermion condensed. People might object that fermion cannot condense because it's a fermion. But what we can do is to actually bring a bunch of physical fermions, real fermions, other than the degrees of freedom, in the toric code, and then pair condense them with the quasi-particle fermion from the bulk. I forgot to cite some papers. The papers by Shengjie Huang and Drew Potter, I think, also on this fermion condensation boundary. So this can be written down in exactly solid models, and everything can be made explicit. But after that, we can still choose the M-string operator to be the Z2 symmetry, because that's still left to toggle between 1 and -1. But then the charge that can tunnel become the fermion, because the fermion is now condensed on the top boundary, and it can tunnel to the bottom boundary and become the symmetry charge here. And of course, that's because we want a 1 + 1D fermion system. And then the two phases that we're interested in are related to, again, the condensate of E and M on the bottom boundary. And correspondingly, we have the trivial superconductor and the Majorana chain being the two topological version of the superconductor. And we can see that when the fermion tunnel down, they become excitations in either. So these are literally just the superconducting state with the quasi-particle fermion. So this sandwich with the change of top boundary, we realize these two different phases between topological and non-topological superconductors. And you see that these two pictures, they're very much related, except that we change the top boundary from the fermion condensate to the gauge charge condensate, or vice versa, and we toggle between 1D Ising chain and this superconducting chain. And this is famously, of course, just gauging. Yes.
I thought there were only two possible gap boundaries for the toric code. So what is this superconducting boundary?
Yes. So there are two boundaries if it's a bosonic system. If it's a fermionic system, then there's this extra possibility of fermion pair condensing. If we add physical fermion, literally fermions, Majorana modes, to the boundary, then we can have this third boundary.
So is the toric code different microscopic?
Yeah, if we allow physical fermions, if we literally in the degrees of freedom allow fermions, then we can have this third boundary.
So if you condense the bound state of the emergent fermion.
1 second. Okay.
Sorry, I wonder how you identify the result as a trivial superconductor.
Right.
Do you really check the lattice model, the microscopic degree of freedom really match?
Yeah, so here the argument is very simple-minded, just saying that because the fermion, when you tunnel down, it becomes an excitation. So there's no somehow symmetry breaking. Of course, with fermion, there's no symmetry breaking. But then you might ask, which one is trivial, which one is non-trivial? In this setup, it's actually hard to tell. You really need to write down the lattice model, and for each one expose the boundary and see. And it very much depends on the details of how the top boundary is written. So it's actually quite tricky, and that's actually a very important insight that we're using to write another paper, which is we need to put it out. That these two boundaries, they're actually not that different, meaning that when we use the sandwich structure to realize the trivial and topological superconductor, they're not that different. These are the so-called invertible topological phases, and well, I can spend another half hour on it. So that's a great question. I'll get to you later. Yes, Mike.
So just to follow up on Mike's question, is what we're doing here on the top boundary condensing a composite of a local fermion and the emergent fermion?
Yes, yes, exactly. So there's some terms that can be written down. And this, of course, as Sakura pointed out, this is just Jordan-Wigner, in other words, gauging the Z2 symmetry. But in the sandwich picture, it has a very nice interpretation of just changing the top boundary condition from one to another to implement this gauging transformation. And of course, associated with that, there's the understanding of how the critical points are related. The critical point is known as in both cases, it's the Ising CFT, but there's a slight difference in the two versions. In the spin chain version, the partition function is a sum over the trivial sector and the energy sector. and there's a charge sector, and then the total partition function will be the sum over all three. This is the sector with no charge. This is the sector with charge. And then the total Hilbert space is a sum over the two parts. And then on the fermion side, it's the same CFT, except that now we sum over the trivial part and together with the fermion charge part, because the charge becomes the fermion charge. So we need to sum over the fermion charge and then get to a slightly different partition function. This is, of course, also very well understood in a paper by Anton. I think I cited Anton back in the days. So these are all parts of the same CFT, except that we need to reorganize them into different versions of so-called modular invariant partition functions. And I'm running out of time, actually, sorry. There are more examples. Let me just give one more example of this. Yes.
When you added the other fermion, did you make the theory a fermionic theory or not? Because the original toric code is a completely bosonic theory.
Completely bosonic spin model.
Sorry?
Completely bosonic spin model.
Right, so you can put it on any manifold independent of spin structure and all that. Great, but when you added another fermion, is this still true or not?
This is 1 plus 1D. we can, so this lattice model of fermion, and you might say, oh, there needs to be a spin structure. This is 1 plus 1D, so I think we're...
Well, they still depends on the spin structure.
Yeah.
But the original model didn't have that dependence.
Yeah, exactly.
Okay, so it's a different...
It's a different system.
Okay, thank you.
There's fermionic degrees of freedom. Right. So let me still very quickly go through the second example, because then I want to arrive at a general picture. So the second example is Z2 cross Z2. So we just take 2 copies of toric code. And then we condense all the gauge charges on the top boundary to achieve the gap boundary on top. And then the symmetry operator can be chosen to be the string operator associated with the flux, and gives us Z2 cross Z2 symmetry, and then the charge is tunneled down as still the charge of the effective sandwich. And then the bottom boundary can be chosen to be different things. It can be chosen to be just a pure flux condensate, or it can be chosen to be some modified dion composite condensate. But the key, again, is that the charge, when it tunnels down, it's still an excitation, right? It doesn't disappear into the condensate. So either of these phases are so-called symmetric phases. There's no symmetry breaking happening. So this turns out to be the trivial and non-trivial SPD. Of course, which one is trivial, which one is non-trivial is, again, tricky. But at least between them, there's a difference of SPD. And to the transition between the two SPTs under the Kennedy-Sasaki transformation becomes a symmetry breaking transformation, and that can be understood as very well explained in a paper by Mengcheng and Shenjie, is that we can simply choose the top boundary to be a different boundary, this modified flux condensate, such that now the charge becomes different. The symmetry is still the same symmetry, but the charge becomes different operator, and the charge can disappear both on top and in the bottom, meaning that there's spontaneous symmetry breaking going on and ground state degeneracy induced by the tunneling of the charge in the phase. While on the other side, you see that nothing matches between the top and bottom, so nothing can tunnel, and this is still a symmetric phase. So a very simple rule we use to determine whether it's symmetry breaking or symmetric. And this is, of course, just the Kennedy-Sasaki transformation. And you can simply play with the sectors to get the partition function across the transition. So I think I'll just skip the next example, even though it's a very nice example by Caroline Michael. I did have some questions, but let me get to the bottom. Yes. So let me jump to the general question, general picture. I hope with these two examples, we can see some common structure emerging that if we're given a phase diagram or some phases realized in this sandwich structure where there's a topological order in the bulk and there's some condensation happening on the top boundary, and then we accordingly we can find what's the topological symmetry in the bulk and determine what's the charge operator. So this is the basic setup. And then the phases are given by different condensations, in different ways on the bottom boundary. So this can be A, this can be B. Of course, there's a C on top. And then overall, if everything's gapped, we have two gap phases. Okay. And then the trick to play is to say, okay, I'll choose the top boundary to be the same one as one of the bottom one. And if one of the they're gap boundaries, then the top one is also gapped, and the whole thing is still gapped. And this is what I think Sakura was saying. This is in general called a. Is it because I'm time up?
I think the computer decided that the time was up. Right.
Hard cutoff. Thank you. Okay, it's over there already. Okay, good. Thank you. Okay, I'll be quick. So the trick to play is that right. The trick to play. Where am I? Oh, it's simply to change the top boundary to be the same as one of the bottom boundary. And actually, this is a nice idea already used in one of the paper by Lawrence and Frank, where they talk about how all gap phases through some gauging or duality transformation can become a maximally symmetry breaking phase. So here we have two different phases. We have two different boundaries, and we can just pick the top boundary to be the same as one of them. And then the nice thing happens is that on one side, there's maximum tunneling between the top boundary and the bottom boundary, while on the other side, there's supposedly smaller tunneling, although some cases are different. But most cases, there's less tunneling that can happen. So there's more symmetry breaking going on one side than the other, and the symmetry breaking is strictly contained from one side to the other. So this becomes the symmetry breaking picture. Okay. So there are several cases. One is that one of the condensate corresponds to the regular G symmetry, vec G symmetry. Then that goes back to the usual Landau story that there's a symmetry breaking from bigger group to a subgroup, and degeneracy is number of cosets, and the autoparameter has a low energy degrees of freedom. But there's also other examples that we know where either of them give you a group symmetry. So no matter what you do, it's always a non-invertible, non-trivial symmetry like a rep G or reps other things. This requires us to go to the generalized Landau paradigm of phase transition. Many people already wrote papers about this, but if we want to really make progress in terms of thinking of phase transition, we need more understanding in terms of how to break from a larger category to a smaller category, and what's the number of ground state degeneracy, and how to think about autoparameter and the low energy degree of freedom across the transition, how to write a field theory using them, how to analyze the field theory. And there are a paper by Sakura and the collaborators on autoparameters that was very helpful to me. And also, so maybe people in the audience can comment on what we can do. And then there are yet other cases where A and B are condensates of the same type of anyons, but just condensed in slightly different ways. So So these actually trace back into back to 2012, where people were looking at SPT phases. I'm just pointing out that there are actually cases where even though A, B are different condensates, there are actually no difference in tunneling. Somehow there are maximally symmetry breaking phases that are different in 1+1D for some weird non-invertible symmetries. Okay, that's all I want to say, all I can say. I'll put a summary here. All right, okay, thank you.
Thanks very much, Xie, for this nice talk.
Yeah, I just want to ask, so for example, so have you thought about how to fit the trivial insulator to integer quantum Hall state transition in this paradigm?
Right. I do have a whole nother talk on 2+1D. So in 2+1D, it's more tricky, especially those more topological phases, not the integer quantum Hall, but things like, for example, Wenjie and I have a paper on P+IP superconductor, and we also thought about SPT, Z2 SPT transitions. So in all those cases, in 2+1D, what can happen is that it can be a loop condensate, not just a point charge.
Right, but I doubt that can apply to integer quantum Hall, though.
Integer quantum Hall, we did P+IP, so.
So how to interpret P+IP then?
Right. So for P+IP, I actually have slides. You know I have slides. Right, so I'm not claiming that we're getting anything new out of here, but just a fun picture to look at. So P+IP in the fermionic case, so it's a fermionic system, so we have a fermion bulk, top Z2 gauge theory bulk, and then similarly fermion condensate on the top boundary, and then when we condense flux loop on the bottom boundary, it becomes either the trivial or the chiral superconductor. So it has to be a loop condensate at the bottom boundary. And then we can play the same trick and say, okay, just skip this. And play the same trick and say, okay, we change the top boundary to be the same as one of the bottom boundaries. Okay, so this is the same trick I was playing in 1+1D. But the thing is that now it's also a loop condensate at the top boundary. So what can tunnel are loops. So it becomes this one-form symmetry, and things become more tricky. And you might say, okay, well, what kind of symmetry breaking is going on? Because this is loop condensate, and in what sense you can tunnel or not tunnel loop? So actually, we kind of know there's some signature of symmetry breaking. For example, oh, sorry, I forgot to mention that when you change the top boundary to be a loop condensate, the one side becomes the gauge version, the toric code, the other side becomes the chiral icing. They're coupled to the Z2 gauge field. And then you ask, what's the signature of symmetry breaking? And that we see because on the ground state degeneracy on torus for toric code is 4, well, that for chiral icing is 3. And the difference in ground state degeneracy is a signature that some cases loop can tunnel. In this case, all 4 non-trivial configurations of loops can tunnel. While in here, only 3 of them can tunnel because the last one actually gives you an extra fermion, and as an excitation, you're not in the ground state anymore. So, yeah, we have a similar story of Z2 SPT, but yeah, I can show you afterwards. But this is the basic idea. I'm not claiming that this is useful in any way, just there's something going on.
Let me ask you a question. Could you go back to the slide? I think you mentioned something about describing effective theory, something like, I think you were pointing to a Landau-Ginzburg model.
Sorry.
And so if you have
the original talk.
Yeah,
okay.
oh yeah, yes. So one of the issues, if you start thinking about this, is that you have non-genuine order parameters.
Sorry.
Like, string-like order parameters.
Oh, yeah.
So one question is sort of,
Exactly. That's a
how you
great point.
actually write down something that...
Yeah, so the hope is that we can...
The larger DOF, of course. So.
I'm not sure if this is the page, but yeah. So the non-local one, I understand, they are kind of like the symmetry twist in the system, right? And the hope I still have the hope here, and maybe you can say that if that hope can stand, is that in the Landau paradigm, in the original Landau paradigm, there are symmetry twists, but we only focus on the autoparameter part. So the hope is that with non-invertible symmetry, can we still do that? Can we still just focus on there are still local ones, there are still ones without the string, and they can tunnel, that's the thing that can tunnel. And
I guess you will not distinguish SPT phases then. SPT phases you can't distinguish then, right? Because they're
right. So the idea is to map all SPTs to symmetry breaking.
Okay.
And then maybe we can do something there. Yes.
Okay. There was a question here.
Yeah. Does this sandwich picture always have a duality interpretation?
Yeah. So that's actually the question. Maybe better for the audience. I am okay with all terminology, but some people call it duality, some people call it gauging, or
maybe you should define what you mean by duality.
Sure. So, for example, like the unconventional transitions that don't fit in the Landau paradigm, but you have a SIM-TFT description, then can I always think about it as, mapping onto some conventional transition in a dual theory, like the Tasaki example you gave?
Yeah. People definitely talk about it in that way. I'm being careful here just because I don't know in general what duality means, whether we have a definition of it.
I think in that context, it's just changing the symmetry boundary.
Yeah.
Right? That's what we would call gauging, but I can see Nati is raising his hand, and I'm fearful of what will come next.
Again, I sound like a broken record. Duality should not be confused with gauging. These are two totally different notions. And I'll just leave it at that.
I agree with that, actually.
So I think according to Nati, these are gaugings, not.
Yes, they're gaugings.
Okay, I also agree with that, not to be mean, but what I wanted to ask is the philosophy of always having it mapped to some symmetry breaking transition. Why is that important for you? Why can't I just have transitions of SPTs and so on and so forth?
I think it's a very, I don't know. So with Landau, somehow we felt like, we understand what's going on. We know what is fluctuating, we know what is low energy degree of freedom, and because of that, we feel somehow confident to say there is a smooth path across the transition. There can be a continuous transition. And if in other cases, we somehow have to find a path. Otherwise, we'll just say, they jump between, like a DQCD case. People used to say you have to jump between, or there's an intermediate thing. We somehow need to have a reason to say, if there's a continuous path that can take us through the transition. So somehow with symmetry breaking, that gives us a reason to think that something smooth can happen, something continuous can happen that across the transition. You don't have to go through first order, or you don't have to go through intermediate phase.
But certainly something continuous can happen with going between SPTs.
Yeah, that's definitely case by case. We understand a lot already. I'm saying whether there's an overall uniform way of thinking about that. No.
And I'm happy with the SIM-TFT being that proposed general framework, but why always phrase it in terms of spontaneous symmetry breaking?
So, for example, I think when the Ghent group, Frank and Lawrence, they consider this, the argument, I think, is that's the one, the SSB phase is the one you can, put on a computer and most efficiently model, right? I think that's my understanding. So it's more of a implementation motivated thing. So the question is sort of in this general, I think Sal's question is, can you actually motivate the SSB as a preferred thing also more on conceptual grounds?
Yeah, exactly. So for SPT, it's like sometimes I know how things happen, sometimes I don't. Like in higher dimension, I don't always necessarily know that there will be a continuous transition. Sometimes we know a mechanism, sometimes we don't know a mechanism. So symmetry breaking is a more, I think, a more straightforward way to say that. And this framework actually, in this sandwich framework, I can always map things to symmetry breaking, but I don't know if I can always map things to SPT actually. It's not guaranteed. Yeah.
So yeah, just to comment on that, I think there's another physical motivation to look at the completely symmetry breaking kind of description, because that's where the field theory is actually kind of the field theory of the excitations. Okay, so the quasi-particles are very simple. So there's a very simple picture of how to build up the full theory out of the elementary excitations of your theory, which are all kind of domain walls. So I think there's a good motivation.
So one more quick question. And I think maybe, Kevin, you can get ready for your slide.
Well, it's more like a comment. So suppose continuity is, or natural continuous phase transition is the goal here, then there are two ways of getting that. I think one is to view it as a Landau. The other just simply viewing it as a change in the sign of the Dirac mass term. So both of them are very, very simple way of getting a continuous phase transition, right? So if the getting a continuous phase transition is the goal, then we don't have to take the symmetry break.
All transitions as included
between SPT, so between the SPT transition, the more natural to view them as like a change in the mass sign of the Dirac Fermat coupling with a gauge field. Yeah. Maybe that's a better approach if we want to ensure some continuity of the phase transition.
Actually, don't know. Yeah, well, we can compare what can be covered, what cannot. That will be another way. Yes.
I mean. Okay, I mean, so in the early days of SPD phase transition, most of the transition is interpreted as a Dirac Fermat coupled with gauge field with the changing sign of Dirac Fermat mass. So that's a more natural way of getting a continuous phase transition between topological states. That I don't know. Sorry. Yeah, I'm just.
I think for non-invertible symmetries, maybe this is the way to maybe approach it. Okay, let's thank Xie again for his nice talk.